The topic today is tests, not graded tests, but the topic of tests as is used in statistics. We will see the practically most widespread framework, which is called the name-and-person framework. That's the one that is used when you will see tests with a p-value. So we'll make sense of this in a few seconds. Tests are used to give a binary answer to hypotheses that, of course, contain some statistical nature. Questions like, is a treatment A better than a treatment B? That's the classical use of tests in medical sciences. For us, for example, when we do QQ plots to see whether we have a normal distribution, it would be more convenient if we would have a test that would answer yes or no. However, as we will see, the tests tend to give a binary answer, but in reality, if we dig a bit more, it's never that binary. That's what we'll try to uncover in this talk. I don't like personally tests very much. There's a large controversy on the use of tests, but and we will discuss why. And I think in many cases, tests are not necessary when we're able to quantify, for example, whether we want to say A is better than B. If we can quantify the improvement of A over B with a confidence interval, then we usually have a better answer. Then is this improvement significant or not can be seen from the confidence interval, for example. So very often, by doing an in-depth performance evaluation with model fitting, like we have seen, we can have better information than a test. Nonetheless, there is very often a number of situations where we have to do tests. For example, we really want to know whether we can use a normal distribution assumption, or also because our reviewers or funding agency or capital providers want some apparently scientific answer on some topics. So we will see how to make sense of all this. We will start by analyzing a few examples. Here is one, for example. Is blue better than red? Blue is, for example, the performance we have for a database management system when we use one of the compiler options. That's an example given here. Then, of course, we can do things like summarizing this cloud of values by a confidence interval for the mean or for the median. And if we find things like this, for example, case 1 on the left, here is the values we find, then we see clearly option 0 has a lower response time than option 1. If we find such values, which we typically have to do if we do our performance evaluation correctly, we don't need a test to answer is red better than B. In fact, we have here a better formulation. We have also some confidence interval for the values here. There are cases, however, perhaps like this one, or this one, where the confidence intervals are largely overlapping. In such a case, the healthy answer should be, well, we're in a gray zone. That's the reality. But sometimes in a gray zone, you do want a binary answer. If you do want a binary answer, we'll do tests. That's the other example I gave. Is this normally distributed? What would you say? No. And this one? Exactly. So perhaps here we'll be happy to have a test for this one, right? So how do tests work? There are multiple variants on the way the tests are defined. Here I'm giving a variant that I feel comfortable with, that I think is scientifically sound. It is what is called the nested model. The nested model means, first, we assume that the data set that we have is generated by a simulator of a certain class of which we don't know the parameter. Sounds familiar? That's the classical statistical approach. So there is a parameter theta that lives in a space, capital theta, which can be very large or very small, depending on the assumptions we're making on the model. But we don't know it. What we have seen is simply an output of this simulator. And then we would like to test two things. Whether, so the truth we want, the ground truth we want about the system is whether the parameter theta lies in some subset theta 0 or not. So there is a null hypothesis. Theta is satisfying some constraints, is lies in a subset theta 0 of all the possible things, and H1 is not of this here. We say it's a nested model because the two hypotheses don't have an exactly symmetric role. This is the complement of this one here, and typically theta is a space which has more dimensions than theta 0. For example, theta 0 is defined by constraint. The mean of this is equal to the mean of that, and theta is the means can be whatever they want. So typically, this has a larger number of dimensions than this. When we're in this set, the theory of set of tests is well understood. In other cases, it might be more delicate here. That's why we call it the nested model. The null hypothesis is the one that we are interested in, typically. Is this treatment improving things or not, for example? Let's take a very, very simple toy example. So it's an example, as we will see, you probably wouldn't do tests for that. We will see why in a few more minutes. But here we're able to do all the maths very simply, so we will understand how things are. For example, I would say, is red better than blue? One way to pose it is to do this. So the first thing to realize is, whenever you do a test or you analyze the results of a test done by someone else, you should do this posing of the assumptions, what test was done. And doing a test means formulating a statistical model with parameters and formulating assumptions on the parameters. Very often this is not done. People say, I've evaluated whether A is better than B. I did, then they give a name of a test, and the answer is yes. But what was this test doing? Are there assumptions behind the test? We will see there are always assumptions behind the test that may invalidate the results if they're not true. Here, one way to pose the test is to say, I assume that the data, the two sets I have, X and Y, are two independent IID samples. Each one is IID. The two are independent, but they are not from the same distribution. The first one comes from a distribution F0, and the second comes from a distribution F1. So that's the general model. And then the null hypothesis considers saying they come from the same distribution. And this non-zero hypothesis means the distribution are different here. I'm cheating a bit when I'm doing that, but that is very often done. Here I'm not really capturing is red better than blue. Instead, I'm testing whether red is different than blue, not better here. So that's a possible case. And you see here the space theta is a very large space. That's all the possible CDFs on a given, all the possible probability distributions on the space in which I'm obtaining measurements. Right? So that is an example of a test. We will see how to handle this one. Here's another variant of this. This one has a name. We will see tests of this kind. But before, let's do this variant, which is called ANOVA model. ANOVA stands for Analysis of Variance. ANOVA model assumes the following model. We assume X and Y are two independent IID samples, but we assume that they come from Gaussian distributions. The first one with a mean mu0 and a variance sigma square, and the second one with a mean mu1 and a variance also sigma square. So the set of parameters of this is all the parameters we find here, which are mu0, mu1, sigma. Right? That's another model. And then we could say they come from the same distribution if, well, mu0 is equal to mu1, and the converse would be mu0 is not equal to mu1. So theta is 0, the subset theta 0 that corresponds to hypothesis H0, the null hypothesis, is the set of parameters mu1, mu0, such that the two first coordinates are the same. Right. This is very often done, but as we can see, there are lots of assumptions made here. What do you think of those assumptions? Are they easy to accept? The same variance. So the first assumption is they have the same variance. So if you have two clouds of points, Do they have the same variance? Well, usually it means they are indistinguishable, and if they are not in the same scale, they probably don't have the same variance already. Also, they are Gaussian, right? So many things are Gaussian, but many things are not Gaussian also. So this is something to be discussed. Nonetheless, this is very, very often used, right? This test here. It's what is called a non-robust test because it assumes Gaussianity of the distributions. We'll discuss robust tests a bit later. This is very often used. It's called analysis of variance because when everything is Gaussian with the same variance here, we are in the framework that we have seen already for least square estimation of the homoscedastic model, when we assume the noise terms have all the same variance. Solving the estimation, the maximum likelihood estimation, is a projection work. It's a least square computation. That can be done in closed form, in matrix closed form. So similar things will occur here for this test. We will see that in fact there is a relationship between maximum likelihood estimation and tests. Fortunately, that reduces our work. This is what's called analysis of variance. Analysis of variance has to do with doing the least square estimation. We will come back to that test in a second. Right now, let me introduce the language of tests. So the first, or the main part of a test is a critical region. So a test is something that takes as input the data, x1, etc., xn, and outputs a 0 or 1, a yes or no, right? Or h0, or we accept h0, or we reject h0, which implicitly means we accept h1. So one way to formulate that is to say for every possible value of the input, I can decide. Since the decision is binary, this is equivalent to defining a subset of all the set of possible outputs of the data. Right? This is called the critical region. The critical region is the set in which we reject H0. So a test is defined by a critical region and must be defined before we have the data. Right? So when you do a test, you say, I apply this test, and the formulation of the test should not be based on the data. It should be based only on meta information about the data. How many samples, what dimension does each sample have, but not the values of the data. Once we have the framework of the data, we use a test. The test gives us a critical region C, and then we see whether the sample we have is in the critical region. And the first thing to remember is critical region means reject. Reject H0. A test is a classifier. So when there's a classifier, there's always two types of errors. In machine learning, they lead to the metrics called recall and precision. Here we have exactly the same thing. They are called type 1 and type 2 errors. We don't know whether H0 is true or whether H1 is true. So if H0 is true and the test, the data is in the critical region, then we make an error. We decide that H0 is not true when in reality it is true. This can always happen, at least for common probabilistic models with non-zero probability. The worst case probability of that, for all cases that correspond to H0, to the null hypothesis, is called the size of the test. So we want it to be small, a few percent. Similar to the confidence interval. When I say the true value of the median of my thing is between A and B with 95% probability, if with 5% it can be off, this is similar for the size of a test. The second type of error, for some reason, consider not the probability of error, but 1 minus the probability of error, and it's called the power function. So the power function is the function that maps for every value of the parameter theta, when H1 is true, the probability of being correct. Because when H1 is true, being in the critical region means we reject H0, we accept H1. So it's the probability of being correct. This would be to be as large as possible. And all the tests that we will do satisfy exactly or asymptotically the property that they are optimal in the sense that among all the tests that satisfy a constraint, so there is a vent that is deciding to show its presence. So of course we have two criteria to optimize. So one way to do it would be to optimize a sum of the two, but we typically don't do it. Here we say, given a size that we want, for example, to be at least 5%, find a test that maximizes the rest. So the probability of being correct when H1 is correct. Okay, perhaps it's just temporary. It's an intentional ventilation. We'll see. Okay, let's try for this test here, and I voluntarily take the simplest case because it's simpler to do the math, where I accept those perhaps weird hypotheses that everything is Gaussian with the same variance. And I want to design a test to test H0 whether the mean is 0. So here I'm doing paired data, so I have only one sequence of data, which is the difference between the performance under hypothesis under condition A and the performance under condition B. And I want to see whether this is negligible, which would mean the mean is 0, versus the mean is larger than 0. Here I'm doing what is called a test that is one-sided. I want to test whether it doesn't play a role versus it plays a positive role. I exclude all other cases. So if it plays a negative role, probably it will be interpreted as H0 being true. Right. So I need to define a critical region. A critical region is whenever I decide that my X, so X are the improvement, A minus B, we want to say whether they are positive. So one simple thing to do is I have n data points, I take the average, and if the average is positive, I will say it's, I reject H0. Of course, simply being positive is not sufficient. I need to put a threshold. So my critical region, I can define it in this way. Does it make sense for you? You became suspicious because of that. It said here. It makes sense. I mean, it makes sense. You want to say, you have to take a binary decision, so you need to aggregate your data. One way to aggregate is take the sample mean and say if the sample mean is, of course, even if the true mean is 0, the sample mean will not be exactly 0, so I take a confidence interval around it. If I'm above some threshold, then it's very unlikely that the true sample mean was 0, since the best we can say for estimating mu is to take the sample mean. That seems quite reasonable. However, if we do that, it's impossible to compute the size of the test, because the size of the test is the probability of failing when H0 is true. H0 is true when we are under those conditions. The unknown parameter is mu equals 0, and sigma we don't know. So I have to compute what is the worst case of the probability of rejecting when H0 is true. So it's the supremum over sigma of this probability. Now, x1 plus etc. plus xn under H0 is Gaussian with mean 0 and variance sigma square. So this is exactly equal to 1 minus the CDF of the Gaussian distribution with variance. Now, what's the variance of all this? It is n 1 over n squared times n, so it's sigma square over n here, which is the same as that, 1 minus the standard normal of c over square root, sigma over square root of n. But the problem is we don't know sigma. Sigma could be arbitrarily large, so the worst case of this, or the supremum of this, is 1. So we cannot define a test that has a size anything else than 1. What was the problem here? The problem is, since we don't know sigma, this thing, finding the threshold is impossible. What is, if sigma is very small, then we should have a small c, because the probability, well, if mu is non-zero, if mu is truly equal to 0, it's very unlikely to see x1 plus xn much larger than c, but the value of c will typically depend linearly on sigma, right? confidence interval we would find depend on sigma. So that was the problem of this test. That shows the issue. So defining tests needs to find a description of the critical region such that we can compute this probability, and it sort of is as much as possible independent of the value. Oh, such pleasure when it stops. So one of the ideas is to try to find a critical region where the thing that's inside here, for example, is what we call a pivot. But the distribution of that is independent of all the free parameters that exist under H0, which is what we can do if we introduce this critical region where Sn is some estimator of the variance, of the standard deviation, Sn squared of the variance. We have seen one of them, for example, 1 over n, the sample variance computed with 1 over n. So if I take this critical region, then if I try to do again the exercise, computing the size of the test, I will have to compute this. And this is if n is large, Sn converges to sigma, so this is approximately Gaussian. That's the central limit theorem. And therefore, this is approximately this. So it's not an exact result, but it's approximately true. And if n is 30 or 40, in most practical cases, this will be true. So this would be the classical ANOVA test we would be for testing whether mu is equal to 0 against mu larger than 0 here. So we will take a critical region of this type, and then the size of the test will be 1 minus the CDF of C, where C is the threshold. Now, to do a test, we need to find the value of the threshold. Which value would you give to the threshold? And the majority says C, because that's the value we've always seen, but we should not be fetishist of 1.96. This is not the correct answer here, because I have a one-sided test. I need to find what's the probability, 1 minus the CDF of the Gaussian, where the 196 comes from a two-sided distribution. We exclude 2.5% at each side of the distribution. That gives 196. When we do it one-sided, we find a smaller value, 165 or 164.49. And we could do this. If we do this, we would have a test of size 2.5%. If we want a test of size 5%, that's the value we would give. So that means for this test, I compute the sample mean, rescaled by this quantity here to make it scale-free, independence of the scale of the data, in fact. And if the result of that is larger than this magic number, 16449, I say, oh no, this deviation is statistically too large, it is significant, so mu equals 0 is not credible. Yes?
What is how we go from Gaussian of 0, 1 to C?
So this is what I call the CDF.
How do you go from that to C?
Oh, by asking MATLAB or looking in a table. Yeah, so the quantile values of the Gaussian distribution, of course, are canonical numbers in statistics. So you have the 97.5 percentile of the standard Gaussian distribution is 196. It's computed numerically. There's no closed form for that. You need to numerically integrate the exponential minus x squared, which doesn't have a closed form. So it transcends. It's an integral that is a function of its own. So it's known only numerically in tables or by MATLAB or other software. Okay. And here, since I'm looking at the 95 percentile, it is smaller than the 97.5 percentile. The famous 6 sigma corresponds to a percentile such that if you take C equals 6, yes, sigma is equal 1, so if you take C equals 6, you will find that n is equal to 0 with 4 nines, I believe, something like that. Right? So it depends on the confidence interval you want to have. Let's look at the converse. The size is what is typically looked at, but let's look at the probability of doing the other type of error. So the other type of error consists in rejecting H0 when in reality it is true. So which is captured by the power function, which is, as we saw before, the worst case value of being in the critical region when we should really be in the critical region, or the best case value here. Now we can do the math here. Now, when we're not under H0, we have two parameters, mu and sigma. So we need to compute what is the probability of rejection when this quantity here is Gaussian, but with mean mu. So I let the mean mu appear such that I have now a standard Gaussian variable. I've subtracted the mean here. So we will see after some math that this is equivalent to this, where the function mu appears in it, right? Which is approximately that. So it's a function of the unknown parameter mu here. I plotted it here as a function of mu. So mu is, imagine you know the truth, so the true difference in the distribution is mu. And the only question you had, is it positive or zero? And here I'm plotting the power function for exactly the test we did before. We would like, ideally, that the power function is at least 95%, because we designed a test of size 5%. We would like that the two errors have the same weight. Perhaps we would like this. We see that if we want this, this is true only if mu star is larger than some value that we can compute numerically, and is around 18 here. Right. Now, what is going to happen if the true mu is below? Well, the probability of, if mu is 5, for example, the probability of deciding that mu is non-zero will be very small. So we're more likely to decide that mu is equal to 0. In fact, we're more likely to decide that when the power is less than 0.5, which is around 9 here. So when we're in the gray zone, the test is very likely to declare mu equal to 0 here. So we can also compute for the data that we had, for exactly the data that we had in the test for this cloud of points here. And I can compute what is the power of the test, and we will find that the power is extremely small. Namely, the power of type 2 error is minuscule here. The problem with tests is that usually we don't know what the power is. So finding the size is the only exercise that is done concretely. Here we find the power is very small, so we're very confident about declaring that mu is equal to 0. Right. But another way to look at it is to say that this value mu star gives an order of magnitude of what I can call the statistical significance value of the test. What does that mean? It means that if the true value of mu is smaller than mu star, then the test is unable to decide correctly. Right? It will decide probably that mu is equal to 0. It has to do with the physical meaning of the test, the resolution of the test. Right? We want to say, is there an improvement in response time? But if there's an improvement of 3 nanoseconds, we don't care, right? Because nanoseconds for us in response time are not important. So we are interested when the response time improvement is order of seconds, for example, if we're talking of a human being interaction. If we're talking of machine-to-machine control things, perhaps we're talking of milliseconds. So for any problem at hand, there is usually a resolution that has to do with the nature of the problem. What are values that we can consider negligibles? What are values that we consider important for the physical nature of the system? That has nothing to do with statistics, just for the physical nature of the system, what are values that are important. Then a test, ideally, should be designed such that the value mu star is larger than the resolution of the test. Otherwise, your test will always declare 0. That's the take-home message. So the statistical significance of a test should be matched with the physical resolution of the data, ideally. In practice, it's very seldom done. This is why people criticize tests. We don't know. We know we reject this, but we don't know whether this test would always reject anything that is physically significant, or vice versa. Ideally, we should do it. So if I think, for example, that my if I redo exactly the test, I could do two things. I could say, instead of fixing the size of the test, I could say, I want to find the best size that corresponds to the resolution of the test. If I care about validly saying things about response time when they are larger than 10 whatever unit, here milliseconds, then the size of the test that I should choose is 17%. If I have a test that has a smaller size, then I'm not able to have that resolution here. Right? This is what we should ideally do. So we should evaluate the two sides of a test and match them. In practice, very often this is not done, so we will have to live with it. When you do a test with MATLAB or with Python, the software will return usually not a binary decision, but a p-value. Why is that? Well, first, we don't, as we will see, the test is not something so binary after all. Let's understand what the story is. For the previous example, we said that the critical region, I capture it with this notation, capital T, I call it the test statistic. It is the thing I number crunch from the output data into something that I will compare with respect to a threshold. This is the formula we found made sense for this test here. And the test consists in computing, once I have the data, the value of the test statistic and compare it to the pre-specified threshold here. Now do a thought experiment. Assume that you redo again you do a replay experiment by drawing X from a hypothetical replay from one parameter that is valid under H0. One parameter that is taken in H0. H0 means I have to specify sigma only, and I consider this probability here. Since I had a pivot, this probability here is independent of sigma squared, so I can plot it here. This is what I did. For every value of t, I can plot what is the probability that a hypothetical replay experiment would produce a test statistic larger than the one that I have seen. Right? So the function that I can plot is this one here. And we see that when I am at the critical value, 1645, the little c, this value here, it means that this probability is exactly 0.05. This is how I designed the test. This is the quiz I asked you a few minutes ago here. But the observation is that, well, the test now says on the x-axis whether the test statistic is above this value. But if I use this mapping here, forget about the capital X for a second, we can view this mapping as simply a mapping from the x-axis to the y-axis to p-values, from t test statistic values to things that are probabilities, so numbers between 0 and 1. T larger than the threshold is the same as the p-value being smaller than 0.05 here. So this is what is called the p-value of the test. The p-value of the test is the test statistic mapped here, and then you go to the y-axis and you call the p-value. So the p-value of x, so x is my data, I call it p star in those lecture notes, is the probability under H0 that another hypothetical experiment would produce a test statistic larger than the one that I have. It's a bit contorted, but this is what it is here. And then what is the rejection region is when we are larger than the threshold here, which in p-value means when we are smaller. So one other thing to remember, p-value small means we reject the null hypothesis here. Why do we do that? Well, essentially because the p-value is defined independently of the size of the test. The value 0.05, as we have seen from the discussion from the power function, is entirely arbitrary. It's done by convenience. Right? So if you rely on a machine telling you yes or no based on an input to the machine, which is a threshold 0.05, of course you have a black box problem. You would like to see why the machine said yes or no. Would the machine continue to say yes or no if the 005 would be 001, for example? All those kinds of answers you would like to have. To avoid this, we return directly the p-value. And the p-value will tell us the information. If t is extremely large, that means the p is very small, we know that we would have the same answer if we would have had a size of 001 instead of 005, for example. So we can judge how confident we are with the result of the test here. In general, this is the general formula for the p-value, as I mentioned. For the example we said before, it will be exactly that. So we computed 1 minus n01 of c. So here I replace c by mu n bar, which is the average of the x. So this is exactly the p-value. So we can see a test software as a machinery that takes the input data x and returns a p-value, number between 0 and 1, which is interpreted as a probability. One confusion, one confusion that's often done about the test is to consider that the p-value is the probability that the test output is wrong. Right? So people in social or medical sciences, they do something, they do a test, does this factor have an impact? We compute the p-value, we find 0.05, so we reject, or 0.01, so it's small, so we reject. H0, we says it does have an impact. And the probability that we are wrong is 0.05 here. But we see it's not exactly that. There are multiple probabilities. We know an upper bound of the probability of being wrong when the null hypothesis is true, is truly upper bounded by the p-value. But the other probability of the other type of error, we don't know where it is. Right? Here is another small question here. So assume I've done a variant of the test I did before, and I found a rejection region of this type. I number crunch my output data through some function t, and I compare the result to some pre-specified threshold. And I assume t is a pivot. Right? What is true about the p-value? And we have a tie between A and B, which is both true because the correct answer is C. Both are correct. If it's truly a pivot, that means the definition of a pivot means this probability, which depends on the parameter theta, does not depend on the parameter theta, because under theta 0, the distribution of t of x is independent of theta. This is what a pivot means. Right? So this supremum is equal to that for any theta. This function is the same for any theta in theta 0. This is what this means here. Right? So if we go more generally, most tests try to find a pivot. Or in fact, the trick of a test is to find a pivot. Very often we don't find one exactly, like I did in the previous test I shown, but approximately. Now, if we assume that capital T of capital X is a pivot, that means P star of X, the p-value, which by definition is 1 minus the CDF of T, where F is the CDF of this thing here, then it is 1 minus the CDF of T of X here. Now there's one trick we have used already. If I give you a random variable y with CDF f, what is the distribution of f of y? It's uniform between 0 and 1. Right? That's the trick we use when we, for simulation, for example, with CDF inversion. I plot uniformly a number, but I draw uniformly a number between 0 and 1, I inverse f, and then I obtain a valid sample of y. So here is the same observation I'm making. The distribution of this, if I put capital X here, is uniform between 0 and 1. So if I have a mechanism to compute the p-value out of any data, if I define a rejection region p star of x less than alpha, that gives a test of size alpha, exactly. Which looks circular. In some sense it is, but at least here it's mathematically proven. So in practice, our job for finding tests will be to find a mechanism to compute a p-value, which means finding a pivot, something whose distribution is independent of the parameter when H0 is true, and then find some mechanics by simulation, by analytics, or whatever mechanism to compute the p-value. And then the test is simply by saying, is the p-value less than alpha? If it is, I reject H0 at size alpha. In this reasoning, there is a large family of tests that is considered on likelihood ratio. So very large family of tests, practically all, not all, but a very large number, is based on maximum likelihood estimation. And for reasons that we will understand now. So assume the nested model like before. Now I can do two things. If H0 is true, that means the parameter lies in the space theta 0. I can estimate the parameter. Estimating the parameter, as we have seen many times, is an optimization problem. We write the likelihood. If we are lucky, we have exponential or Gaussian things, we will have least square or least absolute deviation to optimize. So we'll have to solve an optimization problem. I have to maximize the likelihood or the log of the likelihood. And let me call L and of H0 this thing. X, I put the X here to express that whatever I have estimated depends on the data that I have here. Now I can also estimate under H1. Under H1 here I'm cheating a bit because under the nested model, theta 0 has fewer dimensions than theta. So in terms of Lebesgue measure, in terms of the space or the volume theta 0 takes in theta 0, it is negligible. Right? So if I optimize over this or over that, I will find the same thing. Right? So this is what is classically done in likelihood ratio tests, and this is why the nested model is necessary for this theory to make sense. We estimate the parameters under the big model. Of course, when we do this, we always have this inequality. Why is that?
We are maximizing over a superset. So
exactly. So here we're maximizing over a set that is larger than this one. So we have more space to explore. So we can only, in the worst case, we find the same. But in general, we will find a better maximum. So the difference is always larger than 0. And then the idea of a likelihood ratio test is if the difference is large, then it means that H0 is not true, right? If H0 is true, if the true parameter lies in theta 0, when I add and I explore in a larger space, I will find something that is still in theta 0. Because if I find the true parameter, it will be in theta 0. Of course, since I'm doing estimation, I have an error. I might find something that's not exactly in theta 0, but should not be far from it. So that is what we call the likelihood ratio test. It computes those two things and says I decide to reject when the likelihood difference is very large. It's a difference of logs, so it's also called a log likelihood ratio test. And the question will be how to compute the value of k, and this we will do next week.